Hey everyone, today I'll be going over a simple Leetcode problem, 700. Search in a binary search tree. So we're given a root, which is a node, and some integer value. And basically we want to return the node, find the node that has that value. So if we look at this example, we're given value 2. So you can see the ones in blue. This is actually the tree we have to return. So once we get to this 2, we have to return that node. And then that'll be the whole tree, right? So if you don't know what a binary search tree is, just in brief, a binary search tree is a tree in which every given node, at any given node, all values to the left are smaller, all values to the right are bigger. So you can actually check that in this tree here. So what do we got here? So basically we want to search here. So naively, you could actually just search this entire tree, right? And then when we find it, return it. But we actually want to leverage the properties of a binary search tree because we actually can do this in log n time. The other way would be n time. So we can actually cut out half of the search space every single time. So that's why it's log n. And we'll talk about that later. But basically, what we want to do is we first want a base case. If we ever get to null, we're going to return null. So if we can actually look here, if no such node exists, return null. If we ever get root equals null, that will mean that this value does not exist in this tree. And I'm going to show you why. Because of this property, at any given node, we know that if it's less than the current root, we have to search left because it has to be in the left subtree. If it's bigger, it has to be in the right subtree. If it's equal, then yeah, we found it, you know? So that's what we're going to check. And we're going to first check if the root.value is equal to the current value. If it is, that means that's the one we want. So we're going to actually return root, right? Because this current root's value is value, so that's the node we want. We found it. Else if root.value is less than value, so basically this would mean the value is actually greater than the root value. We know it's in the right subtree. So we're going to take this and we're just going to keep searching. And we're going to go root.right and value. Basically the idea is we're going to keep searching until we find it. I'm going to copy this. And then basically if the just actually what we can do here is we can go else return, yeah, just like that. So we'll go left. So then I'm actually not even sure if you can do this in Java, so I'm just going to run this really quick. Oh yeah, you can. Okay, it just looks strange to me. So basically, yeah, so that's pretty much it. It looks kind of like weird, but basically, you know, is it the value? We return the root. Is it less? Then we keep searching. Or is it greater? Then we keep searching right. If it's less, then it must be in the left. If it's ever null, which basically this means like we get to the bottom and we never found one, it can't exist in this tree because we would have ran across it. So let's just go ahead and submit this. And yeah, it looks like it's pretty good. 100%, 43%. Let's talk about time and space. Time, as I said, is log n. And actually, I'll make this O log n. So it's log n because of what I said, because of maintaining the properties of a binary search tree, we're actually cutting out half of the search space every single time. Because we're having it every single time, it's log n, which is smaller than n. Space will also be for that very same reason. Or actually, the worst case space is really just, well, you could either call it like the max depth of the tree, or you could call it log n. So I'm actually not even going to put anything here, but it's up for interpretation, let's put it that way. So yeah, hope you enjoyed. Thank you for watching.